We do need to spend some time talking about what a measurement is. In class, we use measurements all the time. Whether we're in lecture or in lab, we're using measurements. In lecture, we're using measurements that are usually provided by our textbook or by example problems that we have, maybe by previous experiments done. In lab, we're finding the measurements ourselves. But what is a measurement? A measurement is some type of observation. You can have a quantitative observation or a qualitative observation. Quantitative is a number. It's something that you've measured that has some type of unit to it with a number, though. What I mean by that is when I drive to work, it takes me about 3.9 miles to drive to campus. That's a measurement. I can say I have this many students enrolled in my class. That is the measurement. I can say when I fly home to see my family, it takes me a little over 2 hours. That's a measurement. Those are all quantitative measurements because they all deal with an amount or a number. We can also have a qualitative measurement. A qualitative measurement is what is it? It's the identity of something. Qualitative may be describing the color of a solution and saying the solution is a yellow color or a blue color. Qualitative may be a smell. Maybe it smells like rosemary or it smells like peppermint. Those are qualitative. They don't have a number with them, but they are an observation. Measurements are often compared to agreed upon standards. And so we usually have a standard we're comparing it to make our measurement more accurate. If I am measuring my distance to campus, I'm using the odometer on my car. If I am measuring the time it takes for me to travel on a plane to back home to see my family, I am measuring it based on a watch. So every measurement has a number and a unit. Okay. Now, I want to emphasize by saying that this is most of the time you will have a unit. There are measurements you make that don't have a unit. Like me saying the solution is blue, just saying blue is the measurement. It's a qualitative measurement, it doesn't have a number with that. But me saying it takes me 3.9 miles to get to work, miles is my unit. So most numbers will have a unit with it. There will be cases in class where we see that the number we're measuring does not have a unit, and I will emphasize that when it happens. But we need you to include units when you are giving a measurement because we need to know what you're talking about. If I come to you and say, "Hey, do you want 20?" Well, would you rather have $20 or 20 homework assignments? Because I'd rather have $20 than 20 homework assignments. The unit on your measurement matters. So you always need to state the unit with a measurement. Every measurement also has a degree of uncertainty. So a measurement always has one estimated digit, meaning one decimal place beyond the markings. Let's talk about how we do that. How do we measure that? We estimate the marks by mentally dividing the space into 10 equal spaces. So to talk about this, how we measure, let's go ahead and start with the graduated cylinder first. When I look at this graduated cylinder, the first thing it does say is read the bottom of the meniscus if there is one. Okay? And that's fine. We're going to talk more about that in a future class later on in the semester of why this happens. But the liquid that's clearly higher up on the sides compared to the bottom of the meniscus here, it's an adhesive force. It's because it's very attracted to that cylinder. We can ignore that for now. What is important to know is that it's the bottom of the meniscus here that actually is our true reading on volume. Now, if I zoom in on this cylinder, I can say that with confidence, this is my 4 mil mark. Again, I'm using milliliters to mark the scale, and 5 mil mark here. I can say with confidence I have between 4 and 5 mils. I then look at that cylinder and I see it is marked 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It is marked to the first decimal place. So looking at this, I can say with confidence I have between 4.5 mils and 4.6 mils. The next digit is going to be estimated. I need to estimate what my actual volume is. I know I have 4.5 something. What I do is I mentally break this area up into 10 spaces and I estimate where this meniscus is. Now, some people may say 4.55. That's probably a little higher than halfway through, but it's an estimation. Some people will say 4.55. Probably not. It's probably closer, maybe 4.56, 4.57. 4.58. It's probably not 4.59 because I can see it pretty well. But all of these, sorry, I'm trying to draw these and make or get them out of here so I can make them bigger. These would all be accurate measurements for that graduated cylinder. 4.56. It's an estimate. 4.57, probably a little more accurate. 4.58, probably a little more accurate because it's a little closer to that 4.6 line than not. But it's that last decimal place there, that point zero 0.06, point zero 0.07, point zero 0.08. That is my estimation. That is my un that is my one estimated digit. It's my 1 degree of uncertainty. So what I did was I mentally divided that space by 10 and I estimated that number. Same thing happens on the clock. We can all say with fair confidence that this is just past that 5 mark. Most of us would still say 8:05, but if asked the seconds, we would say 8:05, you know, with us maybe 10 seconds after, something like that. So all measurements do have a degree of uncertainty. Two important terms related to uncertainty of measured values is accuracy and precision. Accuracy is how closely a measurement agrees with the true or accepted value. We have a value that we believe it to be. When we are using a clock is calibrated to have a certain precision to it and to show us the accuracy of the measurement. If we are measuring something with a ruler, we have the ruler has been made to be have a certain accuracy to it, so we can measure to a certain precision. Accuracy, though, again, how closely a measurement agrees to the true or accepted value. Precision is how closely individual measurements agree with one another. We do have random and systematic error that we have to pay attention to as well, but let's talk about just a little more closely here. Looking at a dartboard is kind of the easiest way to see accuracy and precision. In this picture, the goal theoretically of a dartboard is to hit the center bullseye, right? So if you're throwing darts, the goal is to hit that center bullseye. Here, all of my X's are in that center bullseye. I have high accuracy, I'm hitting the bullseye every time. I have high precision, all of my measurements are together. So precision is how closely the measurements align with one another. Accuracy is how close you are to the true value. This here, I see all my values are very close together. That actually gives your measurement a sense of high precision. If I was to look at the deviation of your measurements, they are all very close to each other. They have a high precision, but they're not near the bullseye, so they have a low accuracy. Looking here, if I was to take the average of all of my numbers, they would average out to the bullseye. So they average out to a high accuracy, but the data points themselves are not near each other. They're canceling each other out, which is why we're giving a good accuracy, but they don't have a good precision. They have a low precision because their measurements are not all grouped together. And lastly, low accuracy, low precision. The measurements out all over the place. They're not coupled up together. They're not near the bullseye, they don't average out to the bullseye. We do have two different types of error, random error and systematic error. Random error is just that, it is random. It's due to random fluctuations. We cannot avoid random error. Random error instead is factored out or averaged out by taking enough data points, by taking enough measurements. That's why we often say measurements need to be done in triplicate, because the more measurements you do, the more you minimize that random error within your system. A systematic error is due to limitations in instrument or technique. It's a directional error. Measurements are either too high or too low. So sometimes when we can calculate percent error, most of the time calculating percent error, we just take the absolute value. We don't care the directionality of the error. But let's say we're measuring something and we're always getting a value 5% too low. That is a systematic error. Something is wrong with the measurement we're using. Many, many years ago, I had to get the water pump redone in my car. And all of a sudden, the water pump started shredding my timing belts, which was not a fun thing after I went through 3 timing belts. And it's because when the water pump was made, when they calibrated it, it was calibrated incorrectly and it was off by 1 millimeter. 1 millimeter, which was causing it to shred my timing belt. It was a systematic error in the system. It was not calibrated correctly. Systematic error is very commonly seen when students or humans in general are learning a new technique, especially in the lab. before they get their technique down, before they get really good at what they're doing, they have a systematic error. They're making a constant mistake that's causing a systematic error. Since all measurements do possess some degree of uncertainty, we indicate how much uncertainty with the use of significant figures. In any measurement, some digits are certain and some digits are uncertain. Sig figs count for every certain digit plus the first uncertain digit. The uncertain digit is that estimated digit we have at the end. We can see another example here of accuracy versus precision. If our true mass of if we were measuring, say we're measuring a sample, some kind of mass, and our true mass was right at 10 grams. We see student A has 4 different measurements. The average of those 4 measurements is 10.13. That is not actually close to the true mass. The true mass is 10.00. So 10.13 is pretty far off. And the measurements are nowhere near each other. The student's inaccurate and imprecise. Student B, their average is 9.79, so they are still inaccurate, but they are precise in their measurements. So this is a great example of systematic error. Student A could be systematic error, could be random error, could just be a technique that's not developed yet, or it could be a systematic error. Student C has got great accuracy and great precision, which means they're not showing systematic error. The little bit of difference in their number is a random error, 10.03, 9.99, 10.03, 9.98. When you average those out, you get an average of 10.01 grams. They have great accuracy to their measurements and precision. So this idea of sig figs, we are interested in quantification. We want to know how much. Sig figs were established to help us keep track of precision in measurements once calculators and computers became of regular use. Because calculators don't care about precision or accuracy. They're just going to give you a bunch of numbers. You are responsible for determining what's important and what's not. So some numbers are exact numbers. These are counted as objects, and there are some conversions we're going to see that are exact as well, and I will let you know those as we get to them. But the big thing to know about exact numbers, why they're important, is exact numbers do not limit the number of sig figs we have in calculations. And we will see that come through as we practice our sig figs. For example, in the picture here, I have 5 books. There's no estimation there. It's exactly 5. I have 5 objects. I have 5 books. If I look at the enrollment in my class, I don't know what the enrollment in my class will be, but let's say I have 150 students. If I have exactly 150, that is counted as an object. If I have 153, that is an exact measurement. It's not an estimation. If I have 153 students enrolled, but I say I have about 150, that's an estimation. Okay. But me saying 153 is exact. And again, some conversions are exact as well. So when I'm using like the metric system conversion, so 1000 milliliters to 1 liter is an exact conversion. That does not limit my sig figs. Some numbers are inexact numbers. Any measurement you make is inexact because you are estimating your last digit. So any measured quantity always contains some uncertainty. Again, looking at the graduate cylinder here, let's assume this is on the milliliter scale. I can say with confidence that I have greater than 2 mils and less than 3 mils of liquid in here. I can see that it is marked to 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and 2.7. So I can say with confidence that my measurement is somewhere between 2.6 and 2.7 mils, which means my measurement is going to be 2.6 something mils. When I look at this picture, I would probably say 2.65. It looks like it's about halfway. Someone else may report it as 2.64. Someone may report it as 2.66. We are all correct in our measurement because we are estimating that last digit. All of those, sorry, let me emphasize which ones. All of these are correct measurements because I'm estimating that last digit. It's an inexact number. So what value is each measurement here? Let's assume that this first one is milliliters, this one is degrees Celsius, and this is milliliters. When I look at this first cylinder here, I can see that I've got 70 and I've got 80. So my 70 mark is here, my 80 mark is here. I can see that it is then marked 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That marking is to the ones position. So I can say with confidence, 1, 2, 3, 4, that I have greater than 74 mils and less than 75 mils. Right. Hold on. 1, 2, 3. I can read. Sorry, you guys. I am trying to manage a kitten behind the scenes, and it's there we go. I can say I have greater than 73 mils, which is here. Right? Yep. 1, 2, 3. Yep. And less than 74 mils. But now I need to estimate my digit. I'm going to estimate at the bottom of that meniscus. Now, me personally, I'd probably say I have 73.8 mils. Someone may say 73.9 mils. Someone may say 73.7 mils. All of us are correct. We all estimated that final digit. We broke this space up visually. We broke this space up visually into 10. Okay. So this space up visually into 10, and we estimated where that meniscus was. And then we included our units. So notice that the cylinder is marked to the ones position. I'm estimating to the next position. Looking at the thermometer here, I see my 80 and my 90. We're going to call it that 80 and 90 and not 8 and 9. I don't know what the actual scale is. We're going to say 80 and 90. I can see 85, 86, 87, 88. So I can say with confidence that I have greater than 88 degrees Celsius and less than 89 degrees Celsius. What I need to do is estimate that number now. So 88.4 degrees C, 88.5 degrees C, 88.6 degrees C. It looks like it's about halfway through. All of these are valid measurements for that thermometer. Now, when I look at this last one, it's a little harder to see. I don't see the numbers above, but I do see the 5 and the 6 marked. So I can see 500 here and 600 here. And then there's 10 markings between 5 and 6, which means this marking here is 610, 620, 630, 640. And it's hard to see it, but the 650 is right here. I don't even think I wrote it well. 650 is about right here. So I can say with confidence that I have greater than 640 mils, but less than 650 mils. Now I'm estimating the ones position. So I'm going to say I have 642 mils, 643 mils, 641 mils. Again, it's an estimation. I am estimating that last decimal place. And I'm including my units. So this is something that really throws students off, is this idea of what do we mean to a scientist? When I look here, again, looking at the cylinder, I'm looking at the meniscus, I'm estimating that uncertain digit. To a scientist, writing 2.000 grams is not the same as 2 grams. Me saying, give me 2 grams, that might be 2.1, 2.2, 2.4, 1.8, okay? But saying 2.002 grams is the same as saying 2.004 grams because it's this last digit here that is your estimated digit. I can say with confidence I have 2.00. It's that last digit written down that is my estimation. So even if you're in a lab and you record something off of a balance, the very last digit the balance gives you is an estimation. But all of that is your significant figures. Your sig figs are all of your certain digits, 1, 2, 3, and your first uncertain digit, 4.